Good morning, everybody. My name is Du from Southeast University. Today, I would like to chair this session. The first speaker of our session is Professor Consoli. Professor Consoli is Professor of Civil Engineering at Federal University of Rio Grande do Sul. He is the Vice President of ISEG for the chapter of South America. He serves as AE for Journal of Material and Civil Engineering, ASE GE, and Geotechnical and Geological Engineering. Today, his topic is Consoli's index controlling mechanical behavior and performance of soil stabilized with sustainable binders. So, Professor Consoli, please.
Thank you very much, Professor Du. And so I'm going to start sharing the screen. I will just ask you when it's possible for you to see. Could you just advise me when you are able to see the screen?
Sure. Yes, it works.
Okay, thank you very much. So I will have about 30 minutes to present. And as Professor Du said, I'm going to present an index that is able to control the mechanical behavior and also the performance of soils stabilized. And the idea in the end is to use sustainable binders. So I'm going to show several research that we have been carrying out here in southern Brazil on this area. And I will start talking about my past experiences on solving problems here in South America regarding earthworks where I deal with organic soft soils, sulfated and dispersive soil, loose sands, and even tailings lately. And the idea that I have had was, since I started solving such problems, where instead of adapting my finding, I realized that I could change the mechanical characteristics of them through some physical and chemical stabilization. In other words, I was going to search for ways of changing such characteristics, turning these problematic materials into some materials that I could know the behavior and deal with them to improve solutions. Let me show just some problems that we have here in South America. This is in Paraguay, which is a country right beside Brazil. And even though also in Brazil and Bolivia and in Argentina, we have plenty of difficult soils to deal, problematic soils that are dispersive and also sulfated. We can see here in this embankment that you have this white color. These are sulfates that we have in these soils. Here we have these holes and so that are caused due to erosion because of the salts that you can find also in this that turn the soil dispersive. So one of the ways of trying to solve this is already known, is through soil stabilization. So in this specific case, and in all the cases that I'm going to discuss, most of the cases in the bottom here of the screen, you are going to see a paper that was published on that topic, and also the journal and all the details of the paper. And in this case here, we have used, for example, mellowing and using also some residuals like coal fly ash to improve the behavior of a sulfate-rich dispersive clay that occur here in Paraguay. I'm going to talk about that later. It's just to show some problems that we're going to check. For example, in this specific case, the soil had like soluble sulfates about 14,000 parts per million, which is a huge amount, I would say. And also we have some salts, so it was dispersive, the soil. And in such a problem, we have had to solve problems like this. This was a road that after 6 months of using, you could not see anymore the base of the road, the pavements and anything. Everything was destroyed due to the soil being, in this case, sulfated, and besides of being also dispersive. And here it's written, this is from a newspaper from Paraguay, impassable road, eternal problem in the Paraguayan Chaco, for example. Here are some other pictures that you can also see from also the region, and we can realize about the problems that we have. And it is important to call out that these problems occur in about 6 months after the road was built, just to have an idea. And so we will show also a paper here that was published this last year in Canadian Geotechnical Journal about this material here. Another problem that we have here in Brazil, and possibly even in China you have heard about, was that some incidents that we have had in tailing dams in Brazil. And now 2 years ago, there was a place where we have the failure of a huge iron tailing dams that about 250 people were killed in that situation. And so we started to study these tailings and some others too, and we realized that one of the problems that we have due to the way that it has been disposed upstream dam, and that we can see easily in this stress strain curves, and also here in the stress path. Look, we can see that in the stress path, for undrained stress path, we have the collapse due to the reduction of the effective stress to 0. So we have this static liquefaction in such material. In order to try to solve this problem, we thought about using some binders to improve the material. So this material that we have here that has such a behavior, after inserting some amount of cement, in this case 75 kilo per cubic meter inside the material, we turn the material from material that is liquefiable to a material that is completely changed. I mean, you have some real cohesion, and so it does not liquefy anymore. The concept that we have had for this problem regarding some upstream dams that we have in Brazil that have to be decharacterized because of the problems of the failures that we might have was the idea of using this deep mixing soil right below the dam, the upstream dams in this region, in order to improve them and avoid the possible collapse that we have had in some cases, so avoid future collapses. Another problems that we also have to look after here in Brazil, it are quite common, are like the possibility of using mass stabilization, mainly in highly organic clays. So we can see here that this idea of mixing some kind of cement in the organic clay. And this was a case just to have an idea, this specific soil was in the city of Rio de Janeiro. And in this material, we have about 50% of organic matter content, and the natural water content was ranging between 500 and 600%, the liquid, which was about the liquid limit, so or even above it. So in this case, we have also problems about the sulfate, and we have the pH was quite low. So it was really a difficult soil to deal with. And so we have tested in the lab the idea of inserting some different amounts of cement, and also putting a preload on the top of it. This preload is because of this embankment that is usual to put on the top, because of the difficulty that if you don't have it, to reach the position to improve it. Also, you have a geotextile on the bottom. So usually it's about 1 meter, the thickness of this embankment. So we were also dealing with this, or in the lab, the situation that has happened. What we realized was that using 3 different amounts of cement, 100, 150, and 200 kilos per cubic meter, and without any surcharge, and with the surcharge of 18 kilonewtons per cubic meter, in the end, we can get a unique curve between porosity and unconfined compressive strength of these specimens. This is all published in this paper that was from last year at the Journal of Materials and Civil Engineering from ISEG. Here we also have some results of this unconfined compressive strain test, but also the stress strain curve here, let's say, and then we can see the difference that we have for specimens that are molded in the lab and mixed in the lab, and the ones that were collected in the field. So the difficulty that we have in mixing in the field through this mass stabilization. But even though it gets much better, the unstabilized material that is quite down here. We also have measured the second modulus of these specimens, and we have done like a correlation between confined compressive strain and the second modulus. We have the results from the lab, and this is the red ones that we have here in the bottom are the ones that we have collected from the field data. And so at least they fit exactly the same curve, but as I said, the mixture gets them quite below here. This is a problem of execution of it. But now I'm going to start talking about the idea of sustainability. And the idea of sustainability that we have had in such situations was like to change from the Portland cement or even like lime that it's built in the commerce. And so instead of using those materials, the concept was like going after some residues that could be dealt as cement or transform into cement. And these residues could be from industry, agriculture, even domestic and construction wastes. And the idea was, let's say, to reduce the impact of the cement that we know that is a problem regarding the CO2 production and everything, the production of Portland cement or even lime. And then we went after like looking for novelty or new ways of getting it. And this is a paper that was also published last year about the development of lime after the obtainment of eggshell. And so we have burned the eggshell to certain temperatures and have done, so we have been able to produce both here in the top. We have the material, the quick lime, I would say, okay? And then here in the bottom, we can see in these pictures, the hydrated lime that is transforming, we can get through eggshell. It's interesting also of the amount of lime that you put in a certain soil. For example, this was published in Geotechnique in 2014. But even more interesting than that, we got a patent of a new binder. It was mixing the eggshell with ground glass. Both were residues. And so we have had a new binder that was possible. We can see here in the X-ray diffractometry that we can see here, the formation of a new cement will form tobermorite, which is also formed if you use Portland cement, for example. This was specifically a paper from 2019, also in the Journal of Materials in Civil Engineering. In 2020, here we have a paper that was published at the Journal of Geotechnical and Environmental Engineering from ISEG, and we show this cement cured for 6 or 180 days, and the relation between the initial shear modulus and unconfined compressive strength that we can get. So using in a sand. So we mix this cement with sand, and here we have a fine sand. This is a uniform sand. This is a non-uniform sand, and with different periods of curing and so they have, or they reach some strength. Let's say in this case here about 1.5 megapascal. In this case here, we can even get 6 megapascal, or, sorry, 3 megapascal of unconfined compressive strength and some quite high initial shear modulus using this new cement that is based on residues, let's say. And here we went to the field and we have used this same cement to build some improved bases in which in the top we used to put some shallow footing here. So that was published in 2020, also at the Journal of Geotechnical and Environmental Engineering. So we call it like a green cement using in the field to show how you can really improve. So instead of using Portland cement or even lime in some other cases for clays and so, we are using this cement that was a combination of ground glass, which is a residue, and eggshell lime that was burned and so and built after this quite sustainable line, let's say. We could share this idea. This is a very old paper, but just to have an idea, it's from 2001, about 20 years ago, where we have published. So our research on this area of new cements or things like that, but basically improving the soil, it started in the 1990 decade. So since then, we have been searching and trying to find out how to solve problems with these materials. And instead of using the usual cement that we know that is not it's not sustainable, we have used residues to cement the soil. And using, for example, this was a paper that was published in 2008 on the same concept of using cement and so, but in this case here, we have, let's say, we are gonna put a shallow footing, but it's gonna be pulled out. And so instead of digging a hole here, putting the shallow footing and just insert, for example, sand here, we put sand with some different amounts of cement, and we show that if we pull it out, this was carried out in a centrifuge at the University of Western Australia, where I have been for 1 year in one of my sabbatical licenses. And so we have tested, and we proved that instead, we can see in this figure here, normalized, but this is like the pull-out force that we have here would be about 50. And then if we put 1% of cement in this material that's backfill, we can even double the maximum load. If we put 3% of cement, we can increase to 170, let's say, the load that's normalized here, so the applied pressure, a stress in the end here. And if we put 5% of cement, we multiply by 5 the peak pull-out capacity that we have in this soil. We also have tested some CPT tests inside the centrifuge, showing how it improves and so. So this paper was interesting because we have shown, even though it was in a small scale, the capability of improving this backfill in order to raise the uplift capacity of a shallow footing that we have here. After that, in 2013, we also published the journal. So we have done this in the field, and we have shown also that it's quite interesting, and we have a good solution. Here are other cases in which we improved layers, and then we put shallow footings on the top. We have some numerical analysis showing where the tensile strengths are starts the failure mechanism. That was published in 2019 at the Journal of Geotechnical and Environmental Engineering. But the title of this presentation was like, after so many years of research, we have not had until that moment, and so I call back to 2007, a way of dosing, let's say, the amount of any kind of cement that in our case is not just to insert some kind of binder, but also you have the compaction. So you realize that differently from concrete, for example, in our case, we can control the porosity of the material through compaction. And here we create a new variable, which is the volumetric cement content. And we have proved many years of research looking at it, that we could get an index here that is porosity divided by volumetric cement content that controls initially the strength of these mixes that we have with any kind of binder. But first of all, we use like Portland cement. This paper was published in 2007, and nowadays it has almost 300 citations at Scopus and 250 about that at Web of Science citation too. So just to have an idea in this case, if we have some compaction cures with different energy, and if we choose some points of different dry unit weights and also some points with different moisture contents, using different, so dry densities, using different amounts of cement from 1 to 7%, we can get here a drawing porosity versus unconfined compressive strength for each amount of cement. These are the results for 1%, 2, 3, 5, and even 7%, each one with different porosities. if we put all this data in such a figure here, the unconfined compressive strength versus this index that nowadays we are calling, and it was an idea of Professor Krishna Reddy to call it Consol's index, because I'm going to show you the use of it, not just for strength, but for several mechanical properties, and also the idea of performance, that you can control it through this index here. So as I said, this is a unique curve that we got experimentally. It's a power function. But then in 2017, in a joint work with University of Bristol, we have carried out and we have shown through a theoretical derivation the capacity that we have of this index, theoretical derivation to produce that really shows that the porosity and the volumetric cement content really controls the strength of it. So that was published, as we can see here, in this reference that we have just below here. In 2010, experimentally, we have shown that if you do test unconfined compressive strength or splitting tensile strength, so if you check compression and tension in this case, both varying the amount of cement and also the voice ratio of the dry density. So you have, and showing these results with all these amounts of cement and different dry densities, you get unique curves, one for unconfined compressive strength, for example, and another for splitting tensile strength. And the equations are quite similar. Even the power here is the same. So if you divide the full equation here for a unique sand, but with different amounts of cement and different dry densities, in the end, you get a scalar. And this scalar is the relation for this material here, for this cement. But what is interesting, and that we have shown later, that each soil and each kind of binder, you have for all of them specific values that varies between 0.10 and 0.18. And this is specific for this one. So each material, you might have a different one inside this range. Using now the binder that would be just lime, for example, we published in 2009, idea also that varying the porosity and varying the amount of lime, the volumetric amount of lime, besides it of its support on cement, also this lime, you can get unique curves for strength. Here, it was a paper from 2012 at Geotechnique, proving that besides unconfined compressive strength, splitting tensile strength, we also can control the initial shear modulus of the material based on this same index that we have here, which is also so increasing, not just for strength, tensile strength or compressive strength, but also the stiffness, initial stiffness, shear stiffness in this case, is also controlled by the same index that we have here. For different amounts of cement, different soils, each soil has a specific curve, but it's important to realize that you can get unique curves for each specific soil and each specific cement that you have, but varying the amounts of cement and varying also the complexity, the compaction effort or the void ratio that you have in the end. Another thing that is interesting is that we can realize even from these curves here that you can get let's show this here. You can get a specific strength, for example, varying the amount of cement or lime and the density. You can get a unique strength, for example. And here we got a case in which this relation between porosity and the volumetric cement content was 10, for example, and we have molded specimens that they have the same index, but different voice ratio and different amounts of cement, but they have the same index here. And we realized that after carrying out some triaxial testing, for example, in this case, for a confining pressure of 400 kPa, that the stress strain results was the same. And as I said, this specimen was molded with 0.7 void ratio, and 8.6% of cement, and this 0.8 voids ratio and 10.3% of cement. This was also published in 2009 in the Journal of Geotechnical and Environmental Engineering. So we can say at this moment that besides of unconfined compressive strength, split in tensile strength, even initial shear stiffness, also the whole stress strain curve is controlled. For example, if I have a unique value of porosity volumetric cement content, I can have the same result even with different amounts of voids ratio and different amounts of cement. Another thing that's quite interesting that we have published in 2017, also at the Journal of Materials in Civil Engineering, was that different sands, and we can see here that the shapes are different, the roughness is different, and they are even from different places, and this is from Portugal, this is from southern Brazil, and these are even residues that they have different shapes and so. But they have, they are all in these cases, they are fine grain sands, if we would say. So what we realize we have carried out with different voids ratio, different amounts of cement, different cements, different curing periods, and also compression and tensile strength. And we can see that in each case, for each test, for example, this is a granitic sand from Portugal, and we have tested like compression, confined compressive strength for 7 days and using early strength cement, and we can get a unique curve for different amounts of dry unit weight and different amounts of cement. The curve is the same. And we've tested the Osório sand from Brazil with different cements under compression, also under tension, and different amounts of curing, the different curing times. Though they have, each one, they have their own curve, but we can check it out in this case that the relation, the power that we have in the top here is almost the same. And the real difference would be this scalar that is in front of it. So if we in some way normalize this whole curve through, for example, this green one getting a specific eta CIV 20, for example. So for this one, I get the value of QU or QT, depending what I'm talking about. In this case is QT. I divide the whole curve by this value of QT, and I do the same for the red one. I get this point and divide the whole curve. The blue one, I do the same, and even the pink one. If we do that, we are going to get a unique curve for all these materials. When it's normalized, I mean that doesn't matter the roughness that you have, the angularity of the grains, if it's compression or tension that you have, the type of, in this case, Portland cement, the curve is unique. And this was a breakthrough, also quite interesting, because it reduces the amount of tests that you might have to do to check it out. What is the equation with the scalars for a specific soil or a specific curing period and a specific test, if it's compression, tension, or whatever. There's another work here that so these tests were carried out with sand, and so we have done with some clays and even silts, and so even with the London clay. And this is a paper that Professor Xiaosheng Tang was a co-author to, one of our first papers that we have. It was published at Soils and Foundations, and we showed that specifically for clays, silty materials, so fine grain materials, we also have a specific curve when it's normalized for all these materials. So you have London clay, organic soils, silty soils, dispersive soils, and so on. And we also showed that if you have this equation, that is this one, if you have just one result, for example, from you do just carry out one specific result for unconfined compressive strength, you have 1 point, and you use this curve inserting the point with the eta and CIV specific that you have, you can get the whole curve. These results here were carried out later on, just to check it out if this curve with just 1 point was able to fix about this relation. And also the same we have done with some coal fly ash and cement that we have done just 1 point. We have this curve, and all these other points were carried out later just to check that it was working okay. We have done also some tests with tailings, in which we are trying to. Yes.
Professor Consoli, I'm sorry to disturb you. 1 minute, please.
Okay, I'm gonna go just to finish it. So we have plenty of works that prove that you can use for tailings, in this case in Canadian Geotechnical Journal. And besides of strain and stiffness, also the durability, which is the performance of the material, can be characterized through this index. You can see details at Canadian Geotechnical Journal. You can see also the durability at Journal of Geotechnical and Environmental Engineering. In transportation geotechniques, you have several materials that have tested and they show the same. Besides, just to finish here, to show that also the swelling control of expensive soils also can be controlled through this index that we have here for lime. We have here at Canadian published this year for cement. And also we check it out that this is a paper for cleaner production, that the life cycle assessment also can be checked in ways that you can improve the environmental condition to one or other way of mixing it. And also, finally, we have done some tests to check the cost, and this was published at the journal this year, Journal of Materials Engineering, and we prove that we can get a decision-making model based on this index. So these here are several papers that we have published in the last 3 years on this topic that you can search later if this area interests you. So thank you very much. That's it.
Thank you, Professor Consoli. It's a very impressive theoretic method for analysis data. Because time is very limited, we have to move to the next speaker. If you have any questions, please send an email to Professor Consoli. Thank you very much, Professor Consoli.
Thank you. Thank you.
Thank you.